Welcome to The Explainer. Today, we're going to dive straight into the fascinating world of language models by doing something, honestly, a bit radical. We are going to build one from absolute scratch. We're prying open the black box to see exactly how words get their meaning inside a neural network, and we'll be tracing the mathematics all the way down to a single weight update.
Now, what's really interesting here is how a linguistics theory from way back in 1957 perfectly anchors the complex math we're about to explore. J.R. Firth famously argued that words appearing near each other in text tend to be related in meaning. No human labels are needed for this, and as we're going to see, modern AI is essentially just a massive mathematical manifestation of this exact quote.
Here is our roadmap for today. 1. The problem with words. 2. The first layer myth. 3. Backpropagation and the atom optimizer. 4. Visualizing high-dimensional space. And 5. Scaling all of this up to GPT.
Let's start with Section 1, the problem with words, and exactly why naive approaches just outright fail.
So why can't computers just read text out of the box? Well, every word has to be turned into a number, right? But if you look at the naive approaches, you immediately run into a fatal problem. Assigning integer IDs carries absolutely zero semantic meaning. To a computer, cat is just as different from dog as it is from rain if you're just looking at the numbers 1, 2, and 3. On the flip side, you have one-hot encoding, which gives each word a unique position in a giant array of zeros. But that creates these massive, computationally wasteful vectors, where literally every single word is equally far apart from every other word. There's just no nuance.
So, the crucial takeaway here is that we desperately need a trainable, dense representation that can actually learn relationships. That's where embeddings come in. They fix both of these problems at once. Instead of a single meaningless integer or a gigantic empty vector, we map each word to a continuous, low-dimensional list of numbers.
Moving on to Section 2, the first layer myth, where we expose the black box.
Okay, we really need to bust a major misconception right now. People so often think embeddings are this separate, magical dictionary or some pre-processing step that happens before the neural network even fires up. But in reality, the embedding matrix is the literal first layer of weights in our neural network. It's just a matrix, and it's initialized with completely random values. The magic isn't in those initial numbers. The real magic is entirely in how they change.
Our miniature model for this explainer is incredibly simple. It relies strictly on a lookup table, that embedding matrix E, which then feeds directly into a single linear layer W. That linear layer projects the vector back up to a score across all the words in our vocabulary. Then, a function called cross-entropy loss kicks in, which is really just a strict mathematical way to calculate exactly how wrong the model was in its prediction.
Let's dive into Section 3, backpropagation and the atom optimizer, the actual mechanics of learning. So how do those random initial numbers actually become meaningful? It happens through something called the skip-gram objective. By simply sliding a window over a massive text corpus, we force our model to try and guess what words usually sit next to our target word. If your sense is, I like cats, and your target word is like, the model absolutely has to predict I and cats. And this creates a standard training loop that basically acts as the heartbeat of the entire learning process. First, the forward pass makes a prediction. Second, we compute the loss against the true context word. Third, the backward pass calculates the error gradients. And finally, the optimizer steps in to adjust the weights. And this repeats thousands, millions of times. Tracing this math on a microscopic scale is honestly fascinating. When the target word like tries to predict the context word cats, backpropagation computes the gradients for the whole embedding matrix. But here is the secret sauce. Only the specific row for the word like gets a non-zero gradient. The gradients for literally all the other words remain completely at zero for that specific step.
Next, the atom optimizer steps up. It applies these minute gradients, tracking a running average to adapt the learning rate for each individual parameter. It takes that specific target word vector and just nudges it a tiny bit. Over thousands of these updates, words that appear in similar contexts, like cats and dogs, gradually drift toward each other in this mathematical space. And words with completely opposite contexts, they drift apart.
Now, before we move on, I want to clarify a very common point of confusion. During training, the output of the network is just a single probability distribution over the vocabulary. The network is strictly trying to win a classification game of which word comes next. Finding similar words is actually a completely separate post-training query that we do entirely after the fact.
Which brings us to Section 4, visualizing high-dimensional space, or how we go about flattening the geometry.
We're encountering a pretty unique geometric challenge here. Our miniature embedding matrix assigns 8 dimensions to every single word. But how on earth do you view an 8-dimensional space on a flat 2D screen? I mean, it's basically impossible for the human brain to visualize 8 dimensions, let alone the thousands they use in modern AI. So we need a mathematical trick.
And that trick is called Principal Component Analysis, or PCA. PCA looks at all this messy, high-dimensional space and finds the 2 directions where the data is spread out the absolute most. It then projects all our word vectors straight onto those 2 directions. You can think of it exactly like casting a 2-dimensional shadow of a highly complex 8-dimensional object. When we compare that 2D PCA plot to the true high-dimensional space, we see something pretty amazing. The 2D plot beautifully preserves the large-scale clustering. Cats and dogs are still going to appear grouped together. But it is absolutely vital to remember that it's merely a flattened, compressed approximation of a much richer, high-dimensional reality, where these words are actually interacting on many invisible axes. To truly measure distance in that high-dimensional reality, we rely on cosine similarity. This metric measures the angle between vectors, not their length. Because we care about the direction the vectors point rather than their magnitude, cosine similarity lets us mathematically prove that the vectors for cats and dogs actually ended up pointing in the same direction in that high-dimensional neighborhood. A perfect score of 1.0 means they point the exact same way.
Let's wrap things up with Section 5, Scaling Up to GPT, from the microscopic to the massive.
Let's see how everything we just talked about scales up to the real world. The contrast is just staggering. Our Scratch-built model has a vocabulary of about 16 words mapped across 8 dimensions and trained on maybe a few hundred pairs. GPT-3? It has a vocabulary of over 50,000 tokens mapped across 12,288 dimensions and trained on hundreds of billions of tokens. The scale is astronomically different. But here is the really incredible takeaway. The underlying structure is literally identical. Whether it's 8 dimensions or over 12,000, the input layer of modern LLMs uses the exact same mechanics we just traced. Both use an embedding matrix. Both use gradient descent to update weights. Both map discrete tokens into a continuous geometric space. Proximity encodes meaning, no matter the scale. By deconstructing the basics today, you haven't just learned some cute toy example. You have effectively cracked open the black box of the world's most powerful AI systems. Because understanding our tiny 16-word mini-model means you fundamentally understand the very first layer of every single large language model that exists today.
I'll leave you with this final thought. If an incredibly simple 8-dimensional space can autonomously learn the semantic difference between like and cats purely through mathematical nudges, what hidden, vast, abstract concepts are quietly emerging right now in the 12,288-dimensional space of a trillion-token model? Thank you for joining this explainer, and keep questioning the geometry of meaning.